Thanks, David. So I think Doug is next. I'm actually going to tell a story about Doug. So my first day in graduate school in you were going to tell that story? Should I just let you tell?
No, go ahead.
Okay, so my first day in graduate school in whatever year it was, 1991, 1992, I met with Eric Schwartz, who was going to become my PhD advisor. And it was a very odd meeting because I knocked on his door. He didn't expect me to come, but he invited me in. He sat me down, and he started talking to me about inertial tensors and spherical pointing motors. And I didn't have the faintest idea what he was talking about. And about 10 minutes into our meeting, there was a knock on the door, and it was Doug. And Eric says, no, I'm in a meeting now. You'll have to come back later. And Doug says, I'm sorry, I thought we were supposed to meet now. My name's Doug Greve. And Eric looks at me and goes, if he's Doug Greve, who the hell are you? Anyway, so Doug and I have been friends since then.
Yeah, I think Eric actually said it's Greve. He eventually got my name right, which is good because he was my advisor, and Bruce and I ended up working with Eric Schwartz for the next 3 or 4 years. Eric was, as Marty said, was one of the first people to flatten brains, like literally the way that Marty was talking about. And so that was really my connection to, my first connection to what would be Freesurfer was meeting Bruce as myself, sitting on a couch in Eric Schwartz's office. And so I came to the NMR Center in 1998 and started working with Bruce and Anders, and have been there ever since. And since Bruce stole my funny story, I'll tell you another funny story. So we've run these Freesurfer courses for about 15 years or so, and the second we would run them with a group from Oxford that makes the FSL software. And so the second course that we ran was in Long Beach, California. And the building was actually quite close to the beach. We had signs up everywhere saying FSL Freesurfer course, FSL Freesurfer course. And one day this guy in tank top and thongs and bleach blonde hair shows up and says, hey, I'm here for the Freesurfer course. And I think I was a little disappointed. So I didn't realize that we were supposed to make our talks funny or anything like that. So this is going to be a dry talk. But occasionally maybe I'll pull my ear and everybody can laugh when I do that. So excellent. When I first came to the Martinos now, or the NMR Center, now the Martinos Center, it was to work on fMRI analysis, and I've been doing that now for almost 20 years. But recently, I've moved into the PET world, and so this is a talk about PET MRI integration through Freesurfer, through this package that we just developed called PetSurfer. But it's really a story of how useful the types of thing that Freesurfer is for the neuroimaging community. And so hopefully we can, you'll come out even more convinced how valuable Freesurfer is after this talk. So PET, positron emission tomography, is a way that you can measure things that you just can't measure with MRI, such as energy metabolism and receptor density. And so you get 2 types of studies generally. You get something where you're looking at just uptake, for example, FDG or amyloid or tau, and this is generally just kind of one measurement that's accumulated over 20 minutes or so. And then you also have quantitative measurements, and I put those in quotes because anytime you see quantitative in brain imaging, you should always be a little skeptical. Okay. So that includes things like binding potential, which is a measure of receptor density, or like metabolism. And this has multiple frames, so you're looking at time courses where each frame is about a minute, and they last about an hour to 2 hours. They have to use kinetic models, and these things tend to be just really, really noisy, as I'll show you. PET also has partial volume effects, and I'll show you exactly what those mean. But it's basically like a volumetric spatial smoothing operation And this causes an interaction with anatomy which can cause confounds. And so you need to do partial volume correction. I'll show you what these are in a few minutes. So Freesurfer can help with this because it supplies whole brain and soon whole head segmentation so these are subcortical and cortical representations. So cortically, we have 2D parcellations that are shown here. And we can take all of the subcortical and the cortical and put them together in these really colorful brain maps that show. What's really important here is that they're subject-specific, very accurate maps of the anatomy of the individual. And that's going to be important for doing partial volume correction and processing with the surface, processing the PET. The other thing I want to point out that hasn't really been drawn so far this morning is we can use surface-based smoothing. So instead of smoothing kind of generically in 3 dimensions, we can perform spatial smoothing that respects the inherent geometry of the brain, and with this case for cortex, that's along the surface, and that's going to turn out to be extremely important. So what I'll do is talk about 2 different studies that we did with PetSurfer. One is an ROI study looking at FDG versus aging, and the other is a Voxel study looking at serotonin receptor density. So the first one is this FDG study. So those of you who don't know, FDG stands for fluorodeoxyglucose. It's basically a form of radioactive sugar. And so the subject is injected with this, and that sugar then goes to all throughout the body, including the brain. It goes across the blood-brain barrier, and it gets taken up by cells that are using energy, because it's basically sugar. And then the radioactive element of the sugar decays, and then that's what we end up imaging. And so it's been quite amount of scientific and clinical interest to be able to track metabolism like this throughout their brain with respect to aging, with respect to Alzheimer's disease. And so when I first picked this up, I created PetSurfer, and I basically just wanted some easy study to do to be able to validate it. And I thought, surely people have been studying aging and FTG for like years and years. It must be like completely decided what the effects of age on brain metabolism are, so I can use this as just kind of like write a little paper to just show what the effects are and to validate, PetSurfer, and then I'll have a paper and people can publish it. But it turns out that it was considerably more complicated than that. So this is an example FDG scan. So this is the brain anatomy. This is a simulation of what the ideal FDG scan would be. This is the kind of thing that you get off of the PET scanner. And when you compare these two, you can see that this is really, really blurry relative to this ideal synthesized image. And this is the partial volume, so-called partial volume effect. And it's because the PET scanners don't have the type of resolution that an MRI scanner would have. So these things come out blurry, and it's just like taking this ideal image and smoothing it in the volume in 3 dimensions. And so a typical FDG analysis would work in the following way, where you would take something like a Freesurfer region of interest map derived from the anatomy, and for every region of interest, you would just go and find the corresponding voxels in the FDG, and you would average them up, and then you would do that for every subject, and then you would do, say, a correlation between FDG uptake and age. And this is shown in this map. So everywhere that you have blue, you have decreases in metabolism with age. And everywhere that you have red, you have increases in metabolism with age. And as you can see, there's not any red places, and pretty much everything looks blue. And so what you would draw from this conclusion, from this data, is that there are widespread decreases in energy metabolism as you age. This is from like 50 to 80. But the question is this really real? Because we know that there are strong changes in anatomy, as David Salat was just talking about. There are strong changes in anatomy with age. And so are we seeing a metabolism effect, or are we seeing an anatomical effect here? And to answer this question, you need to have partial volume correction. And so the basic partial volume correction that's used in PET is this thing called the geometric transfer matrix. And it's basically just setting up a linear model of what the FDG image looks like, where you say each ROI is a regressor, and you include some linear smoothing to model the partial volume effects. And then you just solve this linear model, and out pops the FGG signal in the given region of interest free of partial volume effects. And so when you do this, you get a very different conclusion. So here's the analysis without using partial volume correction. You can see that you have all this blue all over the brain, indicating widespread decreases in energy metabolism with age. But when you do the partial volume correction, you come up with a very different story. See, all these frontal areas that are decreasing with age, but the rest of their brain is somewhat free of this. And so this was a little bit shocking to me when I ran this analysis. So we ended up writing a paper describing that when you use no partial volume correction or you use different partial volume correction techniques, you get wildly different results. But I think this result pretty much holds up very well, that these effects that you are supposedly seeing when you don't do partial volume correction are actually anatomical effects that are leaking into the FDG signal because you're applying, the PET scanner is essentially applying this volume-based smoothing. And so why does this happen? You can look at this one. So here's a brain of a 20-year-old, nice, plump, gyri and stuff. When you get to 80-year-old, you can see that things look a little bit different. You have these big ventricles. And you can see that the sulci, there's a lot of space in there now. So now the peel surface is not really pushing up against each other in here. So this is a little cartoon of what I think is happening. So the horizontal axis would be like spatial location, and then here I have gyrus A and I have gyrus B with a little bit of CSF between them. And then the amplitude here is supposed to be the actual energy metabolism. So both gyrus A and gyrus B have a value of 1 there. But what you observe from the PET scanner is this red line here. So you can see this is just simply smoothed by 6 millimeters. And so when you just simply average over gyrus A, you would get a value of maybe 0.7, and gyrus B, you get an average of 0.7 or so. As you get older, these gyri move apart, but they might not actually have a reduction in thickness depending upon where the gyrus is. And so in this cartoon, again, I have the FGG signal is still 1. So there's no actual change in the FGG uptake between this 20-year-old cartoon and this 80-year-old cartoon. The only thing that has happened is that these gyri have moved further apart. No changes in thickness, just the gyri moving further apart. And so again, what you observe are these smooth signals here. But now when you average over this A gyrus, the actual signal has decreased. So this is what's happening, I think. This is this interaction between anatomy and functional signal that we're seeing when we don't do partial volume correction. So when we do partial volume correction, we have to be able to accurately segment where these gyri are. And this is where one of the places where Freesurfer becomes so important because it gives these high accuracy gyral segmentations, cortical surface segmentations that allow us to do this type of partial volume correction and allow us to decouple the function that's being described in PET from the anatomical changes, and keeps us from making these bad conclusions like I was showed on the previous page. So in the second study, it's a somewhat different study of serotonin, the density of the serotonin receptor type 4, so 5-HT4, measured by binding potential. And the way this works, this is a graph. The horizontal axis is time, and the vertical axis is the PET signal. And this blue line here is the average PET signal from from the cerebellum. And then this red line is the average PET signal from caudate. And then you take these two dynamic signals and you do some kinetic modeling on it, and out pops the receptor density in caudate. And so this is a very typical type of way to analyze PET data in order to measure, to give a quantitative measure for the density of receptors. And then you can relate that to function. So this is for an ROI. This TAC, time activity curve, is for an ROI. When you look at it on an individual voxel, things are different. So again, here's this red line, which is the caudate, and then this yellow line is from a single voxel. And you can see that it's extraordinarily noisy. And if you just do a voxel-wise analysis, you end up with something like this. So this is the anatomy, and this is what it looks like if you do a voxel-wise analysis in the volume. You can see, and then the color scale here is the binding potential, which is related to the density of the receptor. And you can see when you look at it on the surface, it just looks like a total mess. Everything is super, super noisy. And so what people have to do then is to apply some type of averaging to it in the form of spatial smoothing. And so when you do that in the volume, you get something that looks a lot more reasonable. You can see that you don't have all this speckle noise here. And then when you put it onto the surface, though, you can see these really strange effects. You can see these things that look almost like somebody was finger painting on the brain. There are these patches that are dark and bright. And this is an interaction between 3D smoothing and the cortical surface. So you're seeing this confound between anatomy and functional signal. And so this is what it looks like on an average of 16 subjects. You can see that this is not a random pattern. This is something that's really following the cortical folding pattern. So you see this, like along superior temporal gyrus here, you see this dark patch, and then it gets bright in the banks and then dark again. You see all this anatomy that's in there. In addition, you can see this bright patch here in insula. And this is caused by a bleed through from putamen. So putamen has a very high 5-HT4 signal. And when you apply 3D smoothing, what you do is you end up smearing the signal from putamen here all the way out into insula, and you get this bright patch. And so these are very bad things, because if you didn't know any better, you would try to start explaining all of the structure in the 5-HT4 pattern as something that's biological, and you might think that insula is actually really bright there. So, but with Freesurfer, since we know where the cortical surface is, instead of smoothing across, kind of blindly across 3 dimensions, we can smooth in a way that follows the native geometry of the surface. And when we do, things look a lot better. So the top surfaces here are standard volume smoothing, and this is with surface smoothing. And you can see that a lot of these patterns you cannot see in the surface-based smoothing, but you can see a little bit there because you still have endogenous partial volume effects inside of the PET. Also, this bright insula spot is mostly gone. And also you can see that it's actually much, much brighter, that when you do 3D volume smoothing, you end up with a lower binding potential because you're smoothing in stuff from gray matter, you're smoothing in stuff from CSF that doesn't have any 5-HT signal in it. And so when you smooth on the surface, you preserve the quantitation that you're working so hard to try to get. But you still have some of these partial volume effects that you can see in here because the PET itself has this 3D smoothing kind of built into it. So even if you're not applying extra 3D smoothing in the form of just spatial smoothing, there's going to be some 3D smoothing that's built into the PET in the form of these partial volume effects. And so there's a different method if you want to do voxel-wise partial volume correction. And so this is a very complex looking flow chart here to describe this voxel-wise partial volume correction method. And I'm not going to go through all of it, except to say that the idea is basically simple. You have gray matter and you have white matter. And when you apply 3D smoothing in the form of a partial volume effect, you get activity from gray matter that's going to be smeared into white matter. And you get activity from white matter that's going to be smeared into gray matter. So the basic idea here is to estimate what the contribution of white matter is and subtract it out, and then measure the gray matter partial volume and go to each voxel and divide it by the gray matter partial volume to bring the scale back up. So you subtract out white matter and then you divide it to get a pure gray matter signal, and then you divide it by the amount of gray matter in a voxel to bring the signal back up to remove the partial volume effects. And when you do that, this is the original volume here. When you do the partial volume effects, you get something that looks like this. And what you can see here are that these zeros kind of in the middle of the brain, in the middle of white matter. And that's because there's no gray matter there. And since you're dividing by the gray matter partial volume, where you don't have gray matter, the signal is undefined. And when you get kind of far away from the center of gray matter, that divisor becomes very, very small, so you get this amplification of noise. And so when you go off and analyze this data, you have a choice of doing volumetric smoothing, or you can do surface-based smoothing. And so you get very different results depending upon which one of those you choose. So here's this grid here. In this column is no partial volume correction. In this column is this voxel-wise partial volume correction. Horizontally, this is volume smoothing, and this is surface smoothing. So this is the original surface that I showed you here. You can see this finger painting all over the cortex and this bright area in insula that's due to the bleed through from putamen. And then this is the surface-based smoothing, where you can still, you've mostly gotten rid of the finger painting and this area in insula, but you still have a little bit of partial volume effects here. This is volume-based smoothing using this partial volume technique. And you can see that what happens is that this gyral pattern that's bleeding through onto cortex is actually getting a lot worse. And the reason for that, if we go back here, is that you have all these zeros. When you do volume-based smoothing, you're taking all those zeros and you're smoothing it into cortex, which seems like a really silly thing to do, but this is actually what happens in the literature. So you end up having, instead of a better partial volume correction, you end up having actually much worse. Things get really, really bad. And so, but when you apply surface-based smoothing, everything looks good. So the reason why surface-based smoothing works here is that what you're doing is you're only sampling at its sweet spot, right in the middle where your gray matter has the most contribution to the signal, and you're avoiding these zero areas, and you're avoiding the edges where you're getting a lot of noise amplification. So surface-based smoothing generally removes surface-based smoothing, along with this partial volume correction, generally removes these partial volume effects. It increases the measure of the binding potential, so you can see how bright yellow this is. So it makes the quantification that much better. So to summarize here, PET requires good segmentation to analyze and correct for these partial volume effects. And I think that for voxel-wise analysis, like my conclusion was that if we're going to do voxel-wise analysis with partial volume correction, it is invalid to do that in the volume. And so this is one of the places where having a surface-based analysis and having Freesurfer becomes, not just helpful and not just nice, but actually critical in being able to analyze your data properly. And I think this is one of the things that makes Freesurfer important. All the anatomy is great and very important, but one of the things that that shows why Freesurfer is so important is because it allows you to analyze these other modalities in the proper way. So there's an interaction in PET between the anatomy and the PET signal through the partial volume effects. And that can create this confound, as I showed before, as you start to work with anatomy that is changing due to disease or age, then it becomes very important to remove the effects of the anatomy from the function so that you can actually get down to what's happening with whatever PET signal that you're trying to look at. And so with all of these things, Freesurfer helps. So use Freesurfer and be happy.